This slide introduces the Universal Capability Analyzer, a powerful tool designed for process capability engineering. While the Supplier Risk Scorecard focuses on supplier-level quality risks, this analyzer zeroes in on the process itself, providing a thorough statistical review of capability. It's the classic CP and CPK analysis that engineers rely on to demonstrate that a process can consistently meet specifications. What really sets this tool apart is its flexibility. It can work with three types of input: raw measurement data, known statistical values like mean and sigma, or even simple defect counts relative to total quantity. No matter the input, it generates a standardized capability report, making it easy to interpret and use. Moreover, the analyzer aligns with established quality standards, including AIAG SPC methodology, ISO 22514, and ISO 9001:2015 Clause 9.1.3. This means its results directly support existing quality documentation requirements without the need for additional formatting or adjustments, streamlining how process capability is assessed and communicated. Let's talk about the challenges engineers face when performing capability analysis. One key issue is that capability questions come up with three very different types of data. Sometimes, we have access to detailed raw gauge data directly from the machine. Other times, suppliers only provide summary statistics like the mean and standard deviation. And occasionally, all we get is a lot size and a count of defects from inspection. Previously, each of these situations required separate manual spreadsheets, each with their own formulas created by different engineers. This lack of consistency and shared validation introduces risks, especially since these CPK values influence critical release decisions. Another point is that manual CPK calculations are prone to errors. Plus, without a visual distribution plot against specification limits, it's difficult to understand which side of the specification, upper or lower, is actually limiting the process capability. Finally, capability studies were typically one-off calculations, with no lasting record tying the results back to their inputs. This means there was no audit trail for future reference or verification. The tool we're presenting solves these problems by unifying all three data scenarios into a single, consistent calculation engine. This ensures the math is the same no matter what data type is used, and every analysis produces a permanent, time-stamped audit record instead of a disposable, one-time result. Let's start by looking at how the capability engine works. It uses three different input modes that all feed into the same statistical core. First, the measurement data mode takes a raw sample grid, then calculates the sample mean and standard deviation directly. This is useful when you have detailed measurement data on hand. Next, the known statistics mode allows you to enter a pre-calculated mean and sigma, that's the average and standard deviation, directly. This comes in handy when, for example, a supplier gives you summary statistics instead of raw data. The third mode is quantity/defects. Here, you input counts of pass and fail items, and the system converts this data into an equivalent CPK value using the inverse normal distribution. This approach aligns with the yield-to-sigma conversion used by industry standards like AIAG, helping to estimate process capability even when only defect data is available. Now, focusing on the core formulas, CP measures potential capability assuming the process is perfectly centered, calculated as the difference between the upper and lower specification limits divided by 6 times sigma. On the other hand, CPK reflects the actual capability by considering how centered the process truly is. It's the minimum of CPU and corporal CPU and CPL indicate which specification limit, upper or lower, is the hardest to meet based on how far the mean is from each limit, normalized by sigma. Lastly, yield is estimated as the probability that a measurement falls within the specification limits, calculated using the cumulative distribution function of the normal distribution. To wrap up, the tool classifies capability using AIAG standard thresholds. A CPK of 1.67 or higher signals high capability, 1.33 or above is capable, 1.00 or higher means marginal, and below 1.00 indicates a capability risk. This standardization ensures that every study's results are directly comparable to industry benchmarks and expected customer or auditor evaluations. here's what the tool delivers. First, the live distribution chart is the most visual feature. It shows the actual bell curve of the process overlaid with the customer's lower and upper specification limits, the plus or minus 3 sigma process voice band, the calculated mean, and the target. This lets you quickly see whether the process is centered and how much margin exists. Next, the full metric breakdown provides all the key numbers an auditor would need, like mean, sigma, CP, CPU and CPL, CPK, yield, and the voice of the process. Each metric comes with a plain language explanation, so even those without a statistics background can understand what the numbers mean. The study library is another great feature. It allows you to save and reload named capability studies for recurring processes or parts, so you don't have to enter data repeatedly. When it comes to exporting data, the tool offers CSV export that includes every raw sample, making it easy to review in Excel or other programs. For a more polished option, there's a native XLSX workbook export, which creates a true two-sheet Excel file with a summary and a detailed sample sheet, complete with real Excel formatting. Finally, the persistent audit log saves every run with a unique run ID, timestamp, and a full compliance statement. This means you always have a complete, traceable record without having to manually retype information into quality documentation later on. This tool is built specifically for the job, not just a quick demo or a generic AI first draft. What sets it apart is how it handles the three real data realities engineers face: raw samples, known statistics, or defect counts. Regardless of the input type, it consistently resolves to the same trusted CPK calculation, ensuring accuracy across the board. One key strength is the correct yield to CPK math it uses. Instead of relying on a simplistic linear estimate, it applies an inverse normal approximation for defect mode, which is mathematically sound and aligns with industry standards. This precision is crucial when converting yield data to capability indices. Another important feature is how it visually communicates process performance. Rather than just outputting a number, it renders the actual distribution chart against the specification limits. This visual representation helps engineers immediately identify which specification limit is constraining the process, providing a clearer process voice. Finally, the tool's exports are standards aligned right out of the box. Whether exporting CSV, XLSX, or audit-ready JSON files, it automatically includes references to AIAG SPC, ISO 22514, and ISO 9001:2015 Clause 9.1.3, eliminating the need for manual additions during audits. This is production-grade engineering logic, robust, precise, and built to support real-world applications, not just a simple mock-up. If you want to compare it directly to other tools, I recommend testing the defect count mode with a small sample, like 3 defects in 1,000 units, and verifying that the CPK conversion matches the standard yield to sigma tables.